Welcome to lectures on deep reinforcement learning. In this video, I will explain how we can use eligibility traces for policy gradient in general and for an actor-critic network in particular. In the actor-critic network with eligibility traces, what we do is we have an actor that learns with a policy gradient method. The critic learns with a TD method. For each of the parameters in the network, actor network, critic network, thresholds, we have one eligibility trace. Eligibility trace is like a shadow variable, like an additional variable. And while we move, we update these eligibility traces for all different parameters. And then at the end of each step, we update the weights and thresholds of the actor and the critic. And the way we do this is we take the eligibility trace and multiply with a TD delta error, the temporal difference delta. So this combines several advantages because it's now completely online on policy, like SARSA in TD learning, or like the advantage at the critic that we have seen before. Compared to SARSA, it has the advantage that we have a policy gradient for the actor, and so function approximation, continuous states don't pose problems, don't pose the same types of problems that arise if we come from tabular TD learning. And then we also have the rapid learning for the critic because we don't have this slow back propagation of information that we know happens in TD0 methods without eligibility traces. So we gain the advantage of an n-step SARSA or other eligibility trace algorithms. Just let me remind you of the basic idea of eligibility traces. Suppose here in this discrete setting, in this tabular setting, on the upper left, we start in a state, we take an action, we go to the next state, another action, another action, another action, until we arrive at the goal, at the terminal state indicated here by the red rectangle. Now, what standard TD0 would do is would update just the Q values of the final transition, the one that's still visible here. With an eligibility trace, however, we keep a memory of previous state action pairs, and this memory decays over time. And the way this memory is implemented is that we have a eligibility trace variable for each combination SA, and this decays at every time step for all the traces. And if an action is chosen, then it's increased by 1. Now, in each time step, we update all the Q values using this eligibility trace, and then we multiply with the TD delta. So let's now use the same idea, but for an actor-critic structure for a gradient algorithm, policy gradient algorithm. So the idea is we keep memory traces of previous candidate updates. And again, this memory decays over time. And the way it's implemented is for each parameter k, we have an eligibility trace, zk, and it decays with a parameter lambda, where lambda is smaller than 1. And this is happening in each time step for all of the traces. And then we also increase, or we update all the traces proportional to the derivative of the log policy. Now, these parameters, the thetas, are finally updated proportional to the eligibility trace and the TD delta. And so now this is policy gradient with eligibility trace. Now in order to, so the difference here is like the bias we have seen, or the baseline we have seen in other policy gradient algorithms. If we express this baseline as a difference of v values, then we need a critic that estimates the v values, and the critic will also use an eligibility trace that's updated with TD lambda algorithms. And so this is now the structure here at the conceptual view, where we have two separate networks. The input, the current state, is called S. Now the critic calculates or estimates the V of S, the value. If it's an estimate, some people put up a hat, V hat of S. So this critic has parameters W. The eligibility traces of the critic have parameters Z with an index W. Our actor network, just to keep the notation different, has parameters theta. The eligibility traces of all these parameters are Z with upper index theta. And then the actor chooses the actions with a policy P, which of course depends on the momentary state S. Now what is this TD delta, the TD error? Well, it's this momentary reward compared to this baseline, the gamma times V of the next state. And from this we subtract the V, the value of the current state, and of course these are also head variables. And so this TD error is used for updates of the weights of the actor, of all these weights over here, but also for the weights of the critic. And if we put this together, then we get this actor-critic algorithm with eligibility traces. Here in the pseudo algorithm adapted from Sutton and Bartow. So ZW, these are the eligibility traces of the critic. Z theta are the eligibility traces of the actor. Then we just run, we run through the maze, we run through the task from step to step. We take our actions according to the current policy. And this policy depends on the parameters theta of the actor. And so while we run through, so we take action A, we observe the next state, we observe the reward, then we calculate the TD error delta, and then we update the two traces, the eligibility trace and the eligibility trace of the critic, the eligibility trace of the actor, and we use these values of the eligibility traces times the delta times the TD error to update the two parameters, and then we go to the next state. So this is the essence of the algorithm. This is now actor-critic with eligibility traces, and let's just finish with a little quiz. Your friend claims the following. Is she right? First claim, eligibility traces are shadow variables for each parameter. That means if you have 2000 parameters in the networks, then I have another 2000 eligibility traces that have to be kept and updated online. Is this correct? And yes, this is correct. The actor-critic with eligibility trace is an online algorithm. Is this correct? Yes, that's correct. Final claim, eligibility traces appear naturally in policy gradient algorithms. Is this correct? Yes, this is correct, but I didn't tell you this yet. So this is going to be the point of a theory part that follows just now. So the claim is that if you do TD learning, eligibility traces are sort of ad hoc. This one version. You can also do n-step TD learning. The claim is if you do it with policy gradient, then eligibility traces turn up naturally. And this is what I will show next.